Okay, so keep up with those notes. I'm as best you can. Now, the notes were not due for today, I don't think.
No, they're due tomorrow.
Due tomorrow. Okay, that's good. I've had to flip flop some deadlines, and you start losing track of when we said what was supposed to be due. So what we are looking at this week is we start looking at chemical bonding. Okay. We had looked at these different elements previously and worked out where they fit on a periodic table by looking at their specific characteristics. But have you ever thought, like, why does it behave the way that they do? Why is it that everything in the same column that we call a specific group that is a particular family, why is it that they have those things that are in common?
They have a valence. They have like a certain number of valence.
Okay, they have a certain number of valence electrons. You're like, what's a valence electron? Okay, that's what we're really going to be looking at with this next section is valence electrons and how they affect the characteristics of a particular element. Okay? I'm going to tell you that pretty much every element on the periodic table, short of a few, are honestly very lonely people that need friends. Okay? That's the way I view them is they are looking for friends to complete their lives because of the valence electrons that they have. You know, it's kind of like days of our lives, but days of our electrons. Okay? So we're going to look at a couple of short videos, kind of to like wrap up the last chapter, transition to this next one, and then we'll start looking at these valence electrons. Okay, so this might be quicker if I go this way, which it probably says you're not even logged in anymore. Ooh, am I? Am I actually logged in? I even might be. I'm shocked. I think that's a first. Every time I try to like get this going ahead of time, it logs me out at the last minute. Might be a little bit better if I actually didn't down the screen. Okay, so let's take a look at this.
Hi, I'm Mr. Ryan from Jackson Middle School.
Now, none of this should be
Today
new.
we're going to talk about how the periodic table is organized. One way you might notice when looking at the periodic table is either metals, nonmetals, metalloids, or even atomic number. We're going to add a couple things to that to help deepen your understanding of the periodic table and its arrangement. It's actually quite fascinating. So let's begin with atomic number. Atomic number moves from left to right. The atomic number is the number of protons, starting with hydrogen, moving to helium, and continuing. It's like reading a book from left to right, and there's a sequence to this number. So, looking at the periodic table, let's just pause for a second and look at Mendeleev and how he contributed to this periodic table and the arrangement of the elements. Mendeleev took all the known elements at the time and placed them on cards. And what Mendeleev did is he laid those cards out, and he started to realize there was a pattern within the elements. Certain physical and chemical properties were repeating. And so what he did was he started to classify those into a table. And so by doing so, he noticed that there was vertical columns that started to emerge to create what we now call a group. And so even elements that were not discovered at the time were later discovered, and they fit the predicted properties that Mendeleev had described. So we actually wrote out cards for the predicted elements, and they fit perfectly.
So what he's describing here is like we talked about how this was kind of like a puzzle, right? Mm-hmm. They looked at all the characteristics of that particular puzzle piece, and they said, okay, well this belongs here, like you would when you're creating trying to solve the jigsaw puzzle. But what Mendeleev was able to do is he took this and he said, oh, I need a piece that looks exactly like this. And so even though he hadn't found the piece, even though he didn't have that element literally right in front of him, he could create a card and describe what that element should be like, and kind of give it its like temporary place. It would be like, literally making up your own little puzzle piece and sticking it in because you lost one. Okay, you don't physically have it, but you can describe it very well. Okay, I really think that everyone should be looking up here right now, not looking at their other screens. So I would, for right now, kind of push this a little close or whatever. You need to be paying attention to what we're doing up here.
Discovered. Now, like I said, these are groups that are vertical, and in the periodic table, in addition to these groups, we also have these periods. And these are repeating patterns that occur in the periodic table based on their physical and chemical properties. So, if we look at the groups, in particular group 1 and group 17, these are the most reactive groups in the periodic table. They're very reactive.
Now, why is it that we have the most reactive in groups 1 and 17? Well, what's the difference between the two of them?
One's
60.
metal and one's non-metal.
So, on the left-hand side, group 1, we have very reactive metals. Group 17 is very reactive non-metals. Why is it not group 18? We don't know why yet. All we know is, hey, those are non-metals too, but 18, noble gases, don't react. We don't know why. We just know that they don't.
Because of the number of valence electrons. We now know that the valence electrons are what make those groups unique. In group 1, they all have one valence electron, all the elements. Group 17 is very reactive, much like group 1. Group 17 is missing only one valence electron, and that group will do just about anything to get that extra electron to fill its outer shell. If we move over here to group 18 has a full outer shell for all of its elements. These are considered the noble gases, and they don't react because those valence electrons are full. And they're
So they're telling us that group 1 has one valence electron only, and group 17 is only missing one valence electron. Do we even know what a valence electron is? Some people that have started their notes already start to know what a valence electron is. How would you describe that, Sydney?
It's the atom of the electrons that has the most the highest energy.
The highest energy. Okay. Is there another way to describe it?
It's the highest charge of electron force.
Well, it has the most force. Again, that's that most energy. How would you describe it if you weren't going to describe it in terms of forces or charges? Like, where are those valence electrons as compared to other electrons?
It's and then it helps determine the chemical properties.
I agree with that, but I'm saying, like, if I were to draw a model of that atom, do I know where I'd be putting those valence electrons in that model?
No.
And that's okay. I'm just saying, like, this is the things that we need to consider. Like, what are these things? Where are they located? Because they're so important. What makes these particular ones important? Are they really close to the nucleus? Are they far away from the nucleus? Do they, like, go in different areas? We don't know yet.
Are happy with that full outer shell. So in summary, let's look at 4 ways we can organize the periodic table. The first way would be metals, nonmetals, and metalloid. That one way
That
is
stair-step
an
region
easy
is
pattern to
metalloids.
recognize when looking at the periodic table. And most periodic tables are color-coded
Or
in this
zigzag.
way. The second way would be atomic number, going in sequence, starting with hydrogen and moving through all the way into the end of the periodic table here, usually in the hundreds. A third way we can organize the periodic table, as mentioned, is by group or valence electron. The outermost electrons in the atomic shell, or the electron shell. And the fourth way being by periods, which represent the number of energy levels in the electron cloud. So,
Ooh. That seems kind of important. Let's back that up.
energy levels.
Energy levels. What energy levels is he talking about?
Oxygen. Wait. How's the first? Isn't it?
Who's the one that described energy levels of an atom? Oops. I don't know if she updated that or not. Who described the energy levels of an atom? Bohr. Okay. Bohr looked at things and he said, okay, we have this nucleus that's made up of these different protons and electrons. Okay. But out here, he said that the electrons are in these different shells or these different energy levels. And so each of these periods, as we go down, the electrons here are just on the innermost level. And the electrons on the next one are the next energy level out. And so this is like the first ring of electrons. This is the second ring of electrons, the third ring of electrons.
So the top is the most lowest energy electron. So you
Yes.
have one valence electron. And
Well, there's not just one electron in each level though. Okay, and that we haven't learned about yet. But I'm saying, right now we have to start thinking about how each of these will correspond to more energy levels. So, because there's going to be more and more electrons. So the electrons get further and further away. They're spaced more, further away from the nucleus.
And the
Let's
electron
finish
cloud.
this up.
So, on your own, choose one group between groups 13 and 18 and try to determine if there are any properties that the elements in these groups share. All right, good luck with this.
Okay. So let's learn a lot more about these valence electrons.
Hi, I'm Mr. Romano from Acton Boxborough, and today we're going to take a look at a special part of the atom, the valence electrons. Think about some of the characteristics that you might have as a person. We know that those come from your genes and your DNA. Well, even though elements are not living things, they do exhibit certain properties and characteristics, and those are derived from part of their structure as well, and that structure is the valence electrons. Let's take a look at an atom. Here's a diagram of an atom of sodium. We know that the nucleus contains the protons and the neutrons, then located around the nucleus are the electrons. We want to focus today on a special group of electrons, the valence electrons. And the valence electrons are the outermost electrons. In my sodium example here, there's one valence electron. I have it in red.
Now, how do I know that there's only this one out there? How do I know that there's only one valence electron? Like, how do I know where they even go? Not a clue, right? How do I know how many electrons this atom needs to have? Period. What has to be equal for an atom to be neutral? The protons and the what?
and electrons.
Protons and electrons, positives and negatives have to be equal. So how do I know how many electrons sodium has? Well, I need to find a periodic table. Okay? With that periodic table, I need to find sodium. And sodium, unfortunately, doesn't start with an S. Sodium, the element on the periodic table is Na. Okay, you'd have to like scan through and look at all the names, or you start learning to, or you memorize, in your head, okay, these are some of the common symbols. Na has 11 protons. Its atomic number is 11. Since the atomic number is 11, it has 11 protons, and I know, hey, this is sodium. So if I have 11 protons, how many electrons am I going to need, Jalen? If it has 11 protons, it's going to have 11 electrons. The two have to balance. So there's going to be 11 protons. We don't know how many neutrons because there can be different isotopes. Okay? But I'm going to need 11 electrons. In this first energy level, the most I can have is 2. And it is full.
Why?
1, 2, and then it's full. That describes the first energy level. That period 1, and those two elements, hydrogen and helium, describe the first energy level. You're like, oh. The next energy level out, I can have 8, which is going to match up my groups 1, 2, and then when we get over here, it's 13, 14, 15, 16, 17, 18. I have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Are you starting to see the pattern? Okay. And then from here, I'm going to go to the next energy level out, and I start placing them if I still need to add more. So right now I have 1, 2, and then 3, 4, 5, 6, 7, 8, 9, 10. Oh wait, that's 8 out there, that's full. So I put 1 out here, there's my number 11. And your valence electrons are always the ones on the outermost energy level. Sodium has 1 valence electron. How could I tell that without drawing a Bohr model? This is known as a Bohr model. Okay, because this is the way that Bohr pictured this to be. Because of the rings. Every time you have those rings, that's a Bohr model. And it's not like 100% correct. It's a model that we use to help us understand, but our understanding later on tells us that, yeah, they're kind of like this, but they're all orbiting in these little shells, that it could be anywhere on a sphere at that sort of distance and space away from the nucleus. They don't stay fixed, just rotating in a circle like they're planets. They could be anywhere on that sphere of that size.
So Bohr was kind of correct.
He was kind of correct, but he wasn't 100% correct. But his model helps us to understand, how many valence electrons we have. And those valence electrons are helping us figure out the properties. So I can do a Bohr model where I can go, okay, how many electrons do I have? And start placing them 2 on the first one, up to 8 on the next one, and then move on to the next one in order to figure out how many valence electrons I have.
So it's like a math problem. Like you
Kind
can
of.
put 2 in the C,
Yep.
and then 8, and then
Now,
the West are.
You want to know an even easier way to find valence electrons for the ones that we talk about this year? You're going to be missing some important stuff. You can, but I'm going to say you're going to be missing some important stuff. Like this is key stuff, right? I think so. So you're welcome to go. Just sometimes things aren't the best time if we can wait.
I have a question. What makes the valence electrons so important once they reach the outer shell?
Okay. The reason why these are the most important is, we're looking at what's going to interact with other things. Like if I bump into someone, if they're holding their books way out here and I happen to bump into them, I'm probably going to cause an interaction, right? If I have everything really close, are they going to be able to do anything?
No.
No. And so it's kind of like that where the ones on the outside, that when 2 atoms come into contact with one another, they're going to be the ones that are going to be interacting first. right? And it's these ones out here where we don't have a full energy level. If we don't have 8, or in the first period if we don't have 2, it's going to want to be complete. It says, oh, I only have 1. I need to do something with this so that I don't have this incompleteness. It feels incomplete. Even though it was a completely stable atom, it doesn't feel that way. And it wants those friends to either have a full outer shell or to, in some cases, give up that valence electron so that it will just have the next most innermost one complete. It doesn't want to have these lonely little valence electrons on the outside. It wants to pair up, it wants to have friends. Okay? And there's an easy way to find this other than drawing a Bohr model. You want to know the other way to find out how many valence electrons atoms have?
Diagram dot.
No, the dot diagram actually isn't. It helps us work out how things pair up, yes. But if I want to know, like, just by looking at it, like, hey, how many valence electrons does oxygen have? Like, I could do a Bohr model, or I can look at the periodic table, and the periodic table will actually tell me.
What about the protons?
It actually has nothing really to do with the protons. The cheat way to do this, and this works for groups 1 and 2, we ignore all of these metals. Okay, we're not really talking about the metals this year other than, yes, they exist. Okay, but when we look at group 1 and group 2, and then groups 15 through 18, if I just look at the ones place of the group number, the ones place of the group number tells me exactly how many valence electrons it has. So everything in group 1 has 1 valence electron. Everything in group 2 has 2 valence electrons. And then I skip over those metals that I say, hey, they're a little bit more complex. You'll talk about them in chemistry, but we're going to ignore them to a large extent for right now. Because things work differently for their valence electrons. When we get to group 13, 14, 15, 16, 17, 18, look at the ones place. Always look at the ones place. Oxygen is group 16. How many valence electrons does it have? 6. Just the ones place. Okay?
Group 1 has 1.
Group 1 has 1, group 2 has 2, because that's their ones place. When I get to fluorine, group 17 has 7.
What about
Group 18 has 8.
what about hydrogen?
Hydrogen has 1. So hydrogen only has 1 on the most inner energy level, but is it complete? No, it needs 2. So hydrogen tries to find a buddy. Okay? Fluorine, group 17, has its first 2 filled in, and then it's going to have 7 over here, and it's going to be missing 1. And it wants to have a buddy. Now, helium, part of the noble gases, group 18, now this is where it's a special case, right? It only needs 2 because it's the first period. That innermost only needs 2, but helium has 2.
So
It's full. Does he need a buddy?
No.
Yes.
No. Helium don't care. Neon, argon, krypton, xenon, radon, they don't care. Their outermost energy level is filled. They have all the valence electrons that they need, whether it's 2 for helium or 8 for the rest. And they're the noble gases. They are like royalty. They're like, I don't need to speak to you, Lord Peons. Seriously. They are very unreactive. Can they make them react? Yes, it takes some special conditions. But in general, they don't react for group 18, which makes the most reactive non-metals group 17. Because all they need is one to be complete. Okay? Group 1, they just have one that maybe they just need to, like, you know, give or take that one, right? So we have these very reactive elements on the almost the outskirts of the periodic table. And as we move in, we have more to either give or more to take, more to share. And all these different atoms will actually do things with their valence electrons so that they can give or take or share. And there's different ways that they share. Okay? And so we're going to be learning about some different kinds of bonds, and I have some really weird mental pictures for you guys to help you remember this. So I want you to think about this as we go through in these future lessons. There's one type of bond that I say they're like the BFFs. Do you know what BFF stands for?
That's right.
Okay, they share really, really nicely. Okay, and that's talking about their valence electrons. Then there's the bullies. Okay, the bullies just literally take the valence electrons away from other elements in order to form their bonds. So we have BFFs, we have bullies, and then one that they don't really talk about so much in the book, but we need to talk about a little bit, I think, is the hippies. The hippies. You're like, what? What do you know about hippies? They're the crazy ones from like the 60s, right?
Yes.
That you hear about in pop culture. Well, they're like peace and love for everyone. They share everything with everyone. It doesn't matter because it's all good. The bonds that we're going to learn about as two different elements try to interact with one another, as I'm looking for a friend, that interaction could be that we share and be friends or BFFs. We could have this, give-take relationship where, we may not be giving quite so willingly, but there's that bully there that's handed over. Or we have the hippies where they're like, hey, I'll just give my electrons to anyone who needs them. Now, this isn't 100% scientifically correct, no, obviously. But are you going to remember if Mrs. Leeson says these strange things?
Yeah.
Hopefully. So I need you to think about, we have to have interactions of metals and non-metals. We could have interactions between two different metals or two different non-metals. Metalloids, kind of like the metals in the middle, it's kind of like a gray area. We're not going to talk about them a whole ton, but we're looking for some generalities so that we can make sense of this periodic table. Okay?
So what if an atom splits?
If an atom splits, that's an entirely different situation. We are not going to be looking at interactions like that. Those are known as nuclear reactions, where what we do is we take particles of different things, like parts of an atom, or even use like neutrons, and we bombard another element with that, and we try to split it apart. And when we do that, we release a whole lot of energy. But we're talking in this next little bit through bonding, where things combine, and chemical reactions where things are acting naturally in the regular world. To get a nuclear reaction where things are splitting apart or really fusing together to form different elements, that takes a very high level physics lab in order to do that. You may. Okay. I think we have a fair amount of time left. Let's finish this up now.
valence electron, I have it in red. And in my oxygen example, I have 6 valence electrons. I've colored those in red as well.
Now, why does oxygen have 6? What group do you think it's in? Group 16. Group 16. It has an atomic number of 8. So it has 8 electrons. 1, 2. It's full. 6 more on the outside. How many more does it need?
2.
2.
If that's just the second shell, what if it gets full and has like, does it make an outer ring?
Well, if this gets full, there'll be another ring.
And then it needs more.
Yeah, but then it wouldn't be oxygen.
Or maybe-
As soon as I suppose it could add electrons, yes, and it's only going to change identity if we change the number of protons. Right? Protons is what changes identity.
These valence electrons are important, in some cases even more important than the other electrons that these atoms have, because they help determine its chemical properties, including things like how it bonds. We know that when sodium comes together with an element like chlorine, it can form table salt, sodium chloride. And in doing so, it's this valence electron right here that gets lost in order to form an ionic bond with the chlorine to make sodium chloride. Now when it comes to my oxygen, if I want to make water, this oxygen can combine with 2 atoms of hydrogen to make H2O, and in doing so, these 6 valence electrons will actually get shared with the valence electrons from the hydrogen atoms in order to form water. So, the valence electrons are important, but it's also interesting to note that atoms with similar numbers of valence electrons have some of the same properties. If you think about brothers and sisters, for example, and how they have some of the same characteristics as other brothers and sisters do, elements are the same way. All elements that have the same number of valence electrons, for example, 1 valence electron like sodium, will have similar properties to sodium. And elements that have 6 valence electrons like oxygen will have similar properties to oxygen. And so we see that these valence electrons are important not just for bonding and for the properties of an element, but also for predicting the properties of other elements with similar numbers of valence electrons. What I want you to do is see if you can find another element that has 1 valence electron just like sodium and 6 valence electrons just like oxygen. And if you can find that information either in your book or on a website, you'll see that those elements have some of the same chemical properties as sodium and oxygen.
Okay?
Because they're in the same.
Because they are in the same group. So, what is going to have the same number of valence electrons as the sodium? What's going to have the same number of valence electrons as sodium? Can I find sodium on the periodic table?
Yes.
Sodium is Na. What's going to have the same number of valence electrons? There's a whole group of them, I promise. Everything that's in the same column as sodium has 1 valence electron. So give me an example of one. Harmony?
Hydrogen.
Hydrogen, yes, has 1 valence electron. What's another one? Christian?
Lithium?
Lithium, yes. Christian Hodges? So we have hydrogen, lithium, sodium, what else? Potassium. Do you know what column we're looking for? Sodium is right here. So So the ones that are gonna have the same number of valence electrons, have everything in the same column. This is a group, and when we're talking about groups 1, 2, 13, 14, 15, 16, 17, 18, we can find the valence electrons by looking at the ones place of the group number. Okay? Potassium, yes. Rubidium, I heard. What's another one?
Cesium?
Cesium
Or
and francium. Okay, all of those have one valence electron, and we found out that they were really highly reactive. Question, Bella?
Yes, and when you say the vacuum, and the atomic mass, it has parentheses and then GTP. Is that like its number?
I don't remember off the top of my head exactly why they put it in parentheses. A lot of the things that you'll see near the bottom there, some of them are more artificially made. Like this is actually not really complete to the current periodic table. This is a slightly older one. That literally this bottom row all the way through 118 is actually all completely named and filled at this point with things that they found or made. But I think that there is some differences as to exactly what is the atomic mass. Like I think partly because some of these are not as natural as others. Okay, so there's some question on that. We're not going to be talking too much about those this year. We're mainly looking at the first ones, some of the building blocks kind of life in the universe, because those all obey the rules that we're speaking of when we're looking at everything that's in groups 1, 4, and then 13 through 18. They tend to obey some very simple rules. Okay? How about something that has 6 valence electrons like oxygen? What other ones have the same number of valence electrons? Jack, can you give me another one other than oxygen?
sulfur.
Sulfur. Okay, Texas, what's another? Selenium. David, can you give me another? I think you're on the wrong period. Or sorry, wrong group. We're asking for ones that have 6 valence electrons similar to oxygen. Can you find oxygen? It's in group 16.
Right by nitrogen. Struck by nitrogen.
Sulfur, yep, we had sulfur, we had selenium. What's another one, Christian? Tellurium. Mm-hmm. So everything in that column has 6. Okay? Now there's another way that we can draw this. Okay, there's another way that we can draw this. We've talked about Bohr diagrams and how they have all those rings. That we're going to see things in like these shells, right? And we said we can find the number of valence electrons by looking at the ones place for the atoms that we're talking about on the periodic table. Now there's one last way that's going to help us understand whether or not they're hippies or bullies or BFFs. Okay? Now we need to start talking about how some electron dot diagrams. They're also known as Lewis dot diagrams. I think that was the person that first created these. Okay, so if I have an atom like carbon, find carbon for me. Find carbon on the periodic table. Okay, so for an electron dot diagram, this is what this is. An electron dot diagram. Okay, I have to start with the symbol for the element. So carbon, it's the letter C. Okay, how many valence electrons does carbon have? 4. So I can go 1, well, or let's keep it as dots, since it is a dot diagram. We're gonna say 1, 2, 3, 4. Okay? So this would be the electron dot diagram for carbon. How about oxygen? Symbol is an O, and it has
6.
how many valence electrons, Jack?
Plus 6.
6? Okay, watch what I do. 1, 2, 3, 4, 5, 6. It's like, we notice a pattern?
Yeah.
How about if I have nitrogen? I have to put the symbol. There's 5. Why? Why is there 5 valence electrons? How do I know that? I'm not saying you're wrong. I'm saying, how do I know that? Who said 5? Okay. So why can't Harmony tell me? I know you know this. How did you find it? You looked at what? Yeah, you looked at the group number, and then from the group number you found the ones place, and you found that it had 5, and that's absolutely correct. Okay? So 5, I go 1, 2, 3, 4, 5. What am I doing each time?
Adding.
I'm adding. Is there a specific way that I'm doing it?
Yeah, you're going clock.
So I'm going clockwise typically, and I add 1 at a time because there's 4 possible locations, and I have to go around and put 1 in each possible location as long as, you know, I have that many valence electrons, and then I come back and I double up. Okay? Typically for this, I can't take this and go, oh, 1, 2, 3, 4. It doesn't typically work that way to start. Okay? We don't do this when we're trying to just look at an electron dot diagram for a single element. Now these can move over time as they start bonding with other elements, but it's good to always try to draw them this way. Okay? You're gonna see oxygen like this, you're gonna see carbon like this. Is it possible that this could switch and move? Yes, it is possible. But I'm never going to have 3 in, you know, I can't go like this. I can't do this. That will never happen. The most I can have in any one location is going to be 2. Okay? Once again, they like to form their pairs. They like to have friends. A lot of the stuff that these atoms are doing, it's because they just need people. They need other elements. You had a question? No? So is this part making sense so far? So these are these electron dot diagrams, and we're going to be using these as we start looking at some bonds. Okay? We talked about bullies. We talked about BFFs. And we talked about hippies. And I said that these share, these take, and these ones are sharing very freely. You know, they're sharing with everyone, not just their BFF, but everyone nearby. Okay? Because that's the way they work. So we gotta figure out with these coming sections, as we look at section 2, section 3, and we learn about the different types of bonds. Have you read anything about any of the types of bonds yet?
No.
Have you ever heard of things like ionic bonds,
Yeah.
metallic bonds,
No.
covalent bonds?
I've heard chemical
Mhm.
bonds.
We have these types of bonds and they'll be coming. We talk about covalent, metallic, ionic, and we don't know from here to here which match. But each of these has a match over here. Does that make sense? Each of these, covalent, metallic, ionic, one of those is one of each of these. So we gotta figure out how to match this up. Now, if I start looking at the names, you have an insight?
Yes.
What?
In metallic, it has the word metal. Maybe it relates how non-metals and metals chemically bond. Because there's a reaction.
Interesting guess. How about covalent? What does co typically mean if we talk about like co-worker?
Like a front
Partner,
work.
You think a hard worker?
like under superior, like a second level.
I thought co-worker was like
A partner.
equal. Co-worker is like someone that you share things with,
Oh,
right?
doesn't that mean the coronavirus is bonding with another virus?
That really has nothing to do with elements. You're looking at things at a biological level, which is much, much bigger. Believe it or not, biological levels are so much bigger. Like what you're looking at a microscope, a regular powered microscope, is huge as compared to the size of an atom. Okay? To look at individual atoms, I need to have a very powerful microscope that really not that many institutions on Earth really have. Like there's usually one at various different universities or research facilities, but they are ones that they will have that one microscope in a room, and that is the reason for that room is that electron scanning microscope. Okay, so atoms are extremely small, much, much smaller than that virus. Okay, but the virus will be made of atoms. Everything, all matter in the world and in the universe is made of atoms. Okay, but here we're going to be matching all of this up. So I think we'll wrap up there today. Make sure you finish up those section 1 notes for tomorrow. We're going to be doing a little bit of review and some wrapping up about valence electrons before we start looking at the bonds. Actually, yes. That sounds wonderful. Keep these, don't lose them.
Why?
Because I don't have replacements for you. Getting a replacement, it would take some time. Don't lose your orange copy. You get to keep it for right now.